Swayam Prabha. Digital India. Educated India.
Good day everyone and welcome to these lectures on physico-chemical processes for wastewater treatment. So, in the previous lectures we studied regarding the advanced oxidation processes and we understood that in the advanced oxidation processes the main objective is to generate various reactive oxygen species and then further use them for mineralization of various pollutants present in the water. Considering the same, there are many techniques which are available which generate these reactive oxygen species in various ways. So, one of the techniques which is very commonly used, it is called as photo-oxidation or wastewater treatment by photocatalysis. So, we are going to learn regarding photo-oxidation or photocatalysis in today's lecture. Now, photocatalysis in general is used not only for wastewater treatment, it can be used for synthesizing various chemicals etc. also. The few things which are common in photocatalysis for reaction engineering or photocatalysis for wastewater treatment, certainly we use a catalyst and also certainly we use some photons to initiate the reactions. So, this is photocatalysis for reaction engineering and wastewater as such are similar, but how they work that we are going to learn in today's lecture regarding the use of photocatalysis for wastewater treatment. The term photocatalyst is a combination of two words we can see, photo which is like related to photon and catalyst which is a substance which alters the reaction rate and thus it enhances the rate of reaction or otherwise the reaction sometimes may not be possible also. So, photocatalysts are material that change the rate of chemical reaction on exposure to light and thus they are known as photocatalysts. Photocatalysis includes reactions that takes place by utilizing light. That light may be of different wavelength and the catalyst generally is a semiconductor which have some properties which via which they absorb light of some particular wavelength. The substrate that absorbs light and acts as a catalyst for chemical reaction is known as photocatalyst. All the photocatalysts are basically semiconductors. So, there is common thing that photocatalysts are semiconductors only and so these semiconductors are like those substances which have an electron hole pair generation on exposure of them to a light. So, any semiconductor material if it is exposed to light in particular depending upon the gap which is there between the valency band and the conduction band, they will generate an electron hole pair. So, this is the common observation for all photocatalysts. Now, there are different types of photocatalytic reactions possible and they may be categorized into two types on the basis of appearance of the physical state of the reactants themselves. So, we have homogeneous photocatalysis and we have heterogeneous photocatalysis. So, we have two different photocatalysis. Now, in the homogeneous photocatalysis the semiconductor and the reactant are in the same phase, that is either they are in gas phase or in solid phase or in liquid phase. and such reactions are called as homogeneous photocatalysis. Now, when both the semiconductor and reactants are in different phases, such photocatalytic reactions are classified as heterogeneous photocatalysis. So, most of the photocatalysis reactions which are used for wastewater treatment, they are heterogeneous photocatalysis. Now, there is one property of semiconductor is that they have band gap. So, that band gap is very essential for generation of electron hole pair, and depending upon the band gap, these semiconductors absorb light of different wavelengths. So, the energy difference between the valency band and the conduction band LUMO band is known as band gap. So, on the basis of band gap, the materials can be classified into three basic categories: one metal or conductor, another semiconductor, and another is insulator. So, those who are having less than 1 electron band gap, so they are called as metal or conductor. Now, semiconductor are those who are having electron gap more than 1.5, but around 3 to 4. So, and up to 5 also. Insulators, they have band gap more than 5 electron volt. So, what does it mean? It means, so here we can see here the insulator is there, semiconductor and conductor. Now, if we start with the insulator, so this is the valency band and this is the conduction band, and here the gap is more than 5 electron volt. So, for providing this much energy, the lambda value which actually is reachable on the earth or otherwise which can be provided, the amount of energy required is very high. So, we despite every mean, it is not possible to transit this electron into this conduction band. So, because we cannot generate any electron hole pair, so this is, they are termed as insulator. In the conductors, the band gap, the energy difference between the conduction band and valency band is very less. So, in fact, very small amount of energy is also good enough to transfer the electron from valency band to conduction band. So, we have generation of electron and holes, but the problem is that electron again will quickly fall back into the valency band. So, electron hole pair which gets generated, that will not be stable. So, it is highly unstable, though the movement is there. Now, in the semiconductors, the band gap electron can move into the conduction band. The energy we can obtain using UV light. The most of the research is going towards utilizing the visible light. Can we create this electron hole band gap? This electron can be transferred from the valency band to conduction band and still they are stable. So, we have a hole in the valency band and electron in the conduction band. If we can stabilize this condition, so that is called semiconductor. So, semiconductors are these materials which have 1.5 to up to 5 or maybe 4 electron volt. So, up to this we can use the semiconductors. Now, going further, how does photocatalyst work? So, when a photocatalyst is exposed to light of desired wavelength is like the whatever is the band gap, it should be able to excite the electron from the valency band to conduction band, that much sufficient energy should be there. So, we have like suppose 3.3 electron volt. So, the this should be equal to h nu, or we can write this should be equal to h c by lambda. So, we can know the lambda value which will be having enough sufficient energy. So, if the photocatalyst is exposed to this desired wavelength which can be calculated from here, the energy of photons is absorbed by the electron of the valency band and it is excited and it goes into the conduction band. Now, in this process a hole is created in the valency band itself. this process leads to the formation of photoexcitation state, and an electron and hole pair are getting generated. This excited electron is used for reducing an acceptor in which a hole is used for, whereas a hole is used for oxidation of donor molecule. So, now this electron can be used for reduction, this hole can be used for oxidation. So, this way we can perform different processes via using this electron hole pair. Now, photocatalysts provide both oxidation as well as reduction environment. So, through this we can work and use them for oxidation of different types of compounds present in the water which are desirable. So, and any undesirable pollutant which is like any organic pollutant. So, if it is present in the water, it can be oxidized via using this technique. Now, interaction of semiconductor. Now, reduction of substrate takes place. So, if suppose we have electron, we have a hole pair which is generated here, and we have a electron which is here. Now, how it will interact with different substrates. So, this is what is shown here. So, reduction of substrate takes place when the redox level of substrate is lower than the conduction band of the semiconductor. So, if the redox level of substrate is this, it is possible because electron can go into this, but if it is at higher state, it is not possible. So, this is the problem. Now, similarly, oxidation of substrate takes place when the redox level of substrate is higher than the valency band of the semiconductor. So, if this is the level, it is possible that reduction will happen, otherwise reduction may not happen. So, under this condition, as we can see, so here it is possible that electron will move from this substrate to this hole and thus neutralize this hole. Neither oxidation nor reduction is possible when the redox level of the substrate is higher than the conduction band and lower than the valency band of the semiconductor. So, this is the state C we can see here. So, we can see here reduction will happen when this condition is there, that for substrate what are its redox level. So, if one of its redox level, higher redox level is lower than that of the conduction band. So, reduction is happening, and this is not possible because this is at lower level. So, it will never go like this. Similarly, in the B stage, the lower redox level of the substrate is higher than that of the valency band. So, the electron can move from the valency band this lower level to this conduction band through this valency band, and it can, this movement is possible, but this movement is not possible because the conduction band level is lower than the higher redox level of the substrate. So, electron can never move into this, but electron can move into this. So, oxidation is possible. In the C level, when both are in between these two levels, so we can see both are possible. So, this is totally redox reaction which is possible. So, this is another condition where both the possibilities are there, that oxidation and reduction both may happen. Now, there is another condition, D condition, where we can see the higher level is above the conduction band, lower level is below the valency band. So, under that condition there is no possibility of any reaction which is possible. So, the key inference is that we should know the gap with respect to semiconductors also, and we should know the substrate redox levels as well. So, if we can perform this calculation beforehand, we can know that whether any oxidation or reduction is possible or not. So, this is there. So, we can see here what is written in the third, that neither oxidation nor reduction is possible when the redox level of the substrate is higher than the conduction band and lower than the valency band, which is like D, stage D. Now, both reduction and oxidation of substrate takes place when the redox level of the substrate is lower than the conduction band, which is here, and the higher than the valency band. So, this is here. So, in the under this condition both oxidation reduction is possible. So, this slide gives an idea that when any reaction is possible, when we can oxidize or reduce any of the pollutant or not. So, this is there. So, we should know the levels, redox level of the substrate as well, which can be calculated. Now, these are the band gaps of different semiconductors. So, we can see here from 1.42 to 3.91. So, for zinc ZNS, so these are different zinc sulfides. So, they have similarly common catalysts which are used in wastewater treatment, they include like zinc oxide, titanium oxide. So, they have this band gap. So, these may vary also. So, they have been reported differently at different temperatures, how they are made, what is their morphology, etc. So, depending upon that, these are the tentative band gaps which have been reported in the literature, they may vary also a little. So, this is there. How do we calculate the band gap of any new semiconductor material or any new photocatalyst suppose we synthesize? So, in this example has been given for mineralization of pyridine and quinoline by copper doped zinc oxide photocatalyst. So, this is there. Now, people are working to use different types of photocatalyst and now to reduce the band gap. So, why they want to reduce the band gap and how they can do this? So, they can reduce the band gap by a doping or using any localized states. There are many possibilities in that, but here we will try to understand that how why they are going for reduction in the band gap, in particular for TiO2 and zinc oxide. So, if we actually perform the calculation for with respect to valency band and conduction band of like zinc oxide. So, whatever is this band gap Eg value, so we can know this Eg value. Now, this Eg value is equated to Hc by lambda, and from this we can calculate the lambda value, okay, by proper unit conversion. So, after putting the values in proper units so that they are reduced, so we can find that lambda value. Now, we will find that the lambda value which is required for performing this electron hole pair, that will be equal to that we require the light in the UV range. That means, we require very high intensity light. Now, the amount of light UV light which is available at the surface of earth is much lower as compared to visible light. So, people want to reduce this band gap. So, they want this valency band to be here, but maybe the conduction band to be here. So, that we can have the lambda which is in the visible light range. So, this is the objective. Now, there is a problem if the band gap gets reduced. So, whenever there is any electron which is moving from here to here, it falls back also very quickly. So, there is a dilemma between how to go ahead, stabilize the system, still use the visible light, and we can reduce this band gap of, suppose this is zinc oxide. So, we can reduce it by doping. So, we have some localized conduction band or valency band created either here or here. So, if we can do this, so this is the reduction in the band gap which is there. So, that is why here copper doped zinc oxide photocatalyst was created, and that has been used for pyridine and quinoline, which are difficult to oxidize compound. So, for their mineralization. So, to understand photo generated electron hole pairs over the photocatalyst, it is necessary to analyze the convenient energy levels or potentials of the semiconductor that is in between conduction band and the valency band edges with respect to potential of the reactive species. So, with respect to reactive is what is the potential, and also we have to know what are their labels, the valency band and conduction band. So, these equations help in calculating the energy gaps of different semiconductors, plotting them for comparison with the standard elements like we can any of these NHE, this we can plot and then we can know. Similarly, we can calculate the homo energy levels of targeted compounds like pyridine, quinoline, etc. So we can understand whether this interaction is possible or not, the way it is shown here in this slide. So, going further, so what we do is that first we try to get the UV versus lambda value, and from that we use this particular equation. So, band gap energy of various zinc oxide sample or any other sample can be calculated using the following relationship, which is called as Stock relationship or Stock plot. And in this what we do is that we plot this particular value with respect to h nu. So, if we can plot this, we can perform the calculation, and this plot is done, and here we take the tangent, and wherever this tangent intercepts the x axis, that value is equal to the Eg value or the band gap. So, here we can see it is tentatively between 3 and 3.5. So, we can take like 3.25 or something. So, this is how we plot them, and thus we can calculate. So, you can go into the literature and study regarding this paper. So, you can use Stock equation, and then also this function is used further for plotting this particular equation, and from here we can calculate the band gap. So, this is the band gap value that we obtain from this plot. So, we can see here different Stock plots are plotted for different doped 1%, 5% doped copper on zinc oxide, and these values can be used for knowing the band gap. So, we can see that with doping the band gap is decreasing. So, there is some optimum doping which will help in reducing the band gap up to a desirable value, so that the semiconductor can be used for mineralizing any compound or otherwise. So, how we know, then what is done is that the interaction, how to understand the interaction, that can be done using these particular equations. So, we can see here for zinc oxide, the valency band and the conduction band, the levels are given here. So, the band gap is 3.3 electron volt. Similarly, for TiO2 also this is given here. So, we can see the whether interaction between them is possible. So, this is for some zinc oxide titanium mix oxide. So, we can know the band gap levels. Similarly, we can here in another condition for copper oxide and zinc oxide. For copper oxide the band gap levels are shown, for zinc oxide the band gap levels are shown, and then for pyridine we can see here, for pyridine their LUMO and HOMO levels are shown, and similarly for quinoline their LUMO and HOMO levels are shown. So, if copper oxide and zinc oxide are mixed together, so we have different levels which are created, and similarly for pyridine, so there are different possibilities of interactions which are possible. So, movement of electron from one place to another. So, using these calculations we can understand the basic mechanism by which the overall interaction is happening. Now, the energy levels of the conduction band and the valency band can be calculated using this equation. So, these equations are used to calculate the values. So, how do we know that what is the exact value of conduction band and the valency band? So, for doing this what we do is that first we calculate the absolute electronegativity of the semiconductor. So, this is done, and this is done using this equation, and here we require the value of A, B, C etc. of the absolute electronegativity of the elements present in the semiconductor as well. So, using this we can calculate the absolute electronegativity of the semiconductor. Now, once this is known and the band gap is known. So, and also the EH2 value, the energy of the free electron at versus H2, this value minus 4.5 electron volt, this is known to us. So, if this value is known, this value is known from the top plot, this value we have calculated above. So, we can calculate the ECB. So, conduction band. Then we can calculate for valency band, so which is equal to ECB plus EG. So, using this equation we can know the exact point, like here for copper it is 1.91 and 0.71. Similarly, for zinc oxide we can calculate 2.98 minus 0.39. So, but this will, we can see this depends upon the band gap value as well. So, through these calculations we can know the energy levels of the substrate, energy levels of the mixed oxides, its different composition, if different oxides within the mixed oxides or doped oxides. So, through this we can understand the basic mechanism as well. Vice versa, if suppose we want to mineralize some key compound, so we can know, calculate the homo level itself, and from the literature we can know how which photocatalyst we should select, so that we have the desired interaction possible via all these 4 possibilities. So, we will select, because we will be knowing the homo level of some targeted compound. So, we should select this photocatalyst in such a condition that interaction is always possible. So, these are the possibilities with respect to use of photocatalyst. So, these are the some of the photocatalysis reactions which are given here. So, like titanium oxide interacting with the desired photon, and then we have electron and hole pair which is getting generated. Now, this hole is again interacting with the water present in the wastewater sample, and then we have H plus and hydroxyl radical which is getting generated. Similarly, this hole is interacting with OH minus, and again a hydroxyl radical is getting generated. Similarly, the electron in the conduction band is interacting with oxygen which may be dissolved in the water to get this particular ion, and this particular ion again reacting with H plus to form another radical. So, these are the different possibilities of radical formation. So, all these radicals which are getting formed, so all these are called reactive oxygen species, and now these will react with organic compounds and degrade them. So, this is possible. Also, there is a direct organic compound may interact with electron and holes. So, we may have reduced product, we may have oxidized product. So, this is direct reaction of the organics with electron and hole pair, and this is like indirect oxidation, where first radicals are getting generated and then they are reacting with the organic compound. So, this is the how the wastewater treatment happens via advanced oxidation processes using photocatalysis. Now, wastewater treatment by photocatalysis, there are few key things to understand. So, organic pollutants, they are sensitive to visible light. Therefore, on exposing it to the light in the presence of some photocatalyst, electron transfer will occur between the organic compounds and the photocatalyst. So, firstly, suppose we take any dye molecule. So, suppose dye molecule adsorb on any of the compound or semiconductor will get excited by absorption of light. Then excited organic pollutant or dye molecule will transfer its electron in the conduction band of the photocatalyst. This excited electron then reacts with the dissolved oxygen to form active oxygen anion radicals. On excitation of photocatalyst, electron hole pair formation will take place, and which is responsible for production of any of these reactive oxygen species, and these species react with organic pollutant to mineralize them. So, the basic mechanism is very similar. There may be, as given here, there may be, this is called direct reduction or oxidation. So, this is there. So, this is direct reduction or oxidation. So, any of these possibilities are there. Then we have indirect oxidation via reactive oxygen species. So, this is also possible. Now, going further, the photocatalytic application of like nano titania promises to be inexpensive via alternative complementary methods for water and wastewater treatment, but there are many challenges which are there with respect to utilizing photocatalysts for large scale application. So, there are many major technical challenges such as optimum system setup, okay, how much water we can process so that the availability of light is still there. So, that is one difficulty. So, we can see here pipes are there. So, in this the titania may be coated and the water while flowing through this pipe gets treated. So, this is there. Also, there are many challenges with respect to utilization of photocatalysts for large scale application, but slowly modules are coming. Now, similarly, the photocatalysis may be integrated with other traditional wastewater system in this manner, that suppose any water is produced which is like it has to be treated. So, we have some physico-chemical treatment here. After that, some photocatalysis is performed so that we can degrade some targeted compounds, and once that targeted compounds are there degraded, the simpler compounds will also get degraded. So, this is possible, and after this treatment it may go to bioreactor for further treatment. So, there are many integrations which are possible of photocatalysis along with the traditional treatment. Now, photocatalytic reactors which are used in the water treatment. The development of new technology can be visualized through the trace of the sun on the horizon. So, we have lot of availability of light from sun, and the problem is that from rising from initial stages during the in the morning. So, there is lot of problem and challenges with respect to photocatalytic water treatment, because like the water treatment using photocatalyst will work only during the daytime and also only between 4 to 6 hours depending upon the availability of sunlight. Second thing, the availability of UV light is not that much. So, we have to see that photocatalysts which are developed, they should be able to work in the visible zone. So, this is a challenge with respect to development of photocatalysts. Then there are other challenges, that we cannot treat highly murkier water because the sunlight will not penetrate into that water. So, that is another challenge which is there. So, there are many challenges with respect to water treatment, and we need to understand all these things. So, there are a lot of studies going on all these aspects, we will not discuss into this, but there you can study many papers and other things to further understand this. Photocatalysis has lot of prospects. We understood that it can be used for wastewater treatment, already lot of research has been carried out. The only challenge is that it will work only during daytime, otherwise we will have to create a simulated atmosphere where the treatment can be done using some artificial lights. Second thing is that we have to use some photocatalysts which can work in the visible light. So, we need to develop those, then only our system can work without utilizing the artificial energy. otherwise we will be requiring UV light from other sources. So, that will make the overall system highly energy intensive. So, with this we will end that today's lecture. We will continue further with advanced oxidation treatment processes, different type, and understand how they work. Thank you.